work Vita-CLIP video and text adaptive clip via multimodal prompting to videos poses a few challenges. Fine-tuning the backbone reduces zero-shot performance. The frozen backbone results in a poor supervised performance. The state-of-the-art methods such as X-CLIP, therefore, have separate training schemes for supervised and zero-shot settings. But the problem with that is that you have essentially two different models. You might as well just have separate architectures for the supervised and zero-shot settings. For unified, supervised, and zero-shot solution, we propose to keep the backbone frozen and then learn multimodal video and text side prompts to adapt the model to videos. We learn frame-level prompts to model per frame information, summary prompt to summarize information across the video clip, video-level prompts to model the data distribution, and textual prompts to enhance text description. And this is our solution to adapt clip to videos. Before we go into the details of our method, we provide a bit of a background on the problem. Contrastive language image pre-training consists of a text encoder and a vision encoder pre-trained on 400 million image text pairs. In this training, images are passed through the vision encoder to produce image embeddings, and text labels are passed through the text encoder to produce text embeddings. And then we optimize the cosine similarity between the correct pairs to improve similarity between the correct similarity between the unmatching pairs. This pre-training results in strong generalization and zero-shot capabilities. And therefore, we have a strong motivation to have it for videos as well. However, in the case of videos, we don't have video text aligned data at the same scale as we have for images. And even if we were to have such data, the computational requirements for such a pre-training from scratch would be much, much higher. Therefore, there's a lot of motivation to adapt an existing image text pre-trained clip model to videos by training it only on a very small video data set. And there are methods like that already exist, like X-CLIP and Action-CLIP, but there are some limitations with these methods that we'll highlight, and then we will propose our solution, which solves for those problems. We already stated earlier that we face in adapting clip to videos is that if you were to fine-tune the clip image and text encoders, it will reduce zero-shot performance because the model will then overfit to the training data set. However, if we were to keep the backbone frozen and just train only a few parameters, then that results in poor supervised performance on the training data set. Therefore, state-of-the-art methods such as X-CLIP tend to have separate training schemes for supervised and zero-shot settings. They normally train for a longer duration on the target dataset for supervised setting, which produces good supervised performance and low zero-shot performance. And then for the zero-shot setting, they train for a lesser number of epochs, which produces low supervised performance but higher zero-shot performance. But the problem here is these are essentially two different models. You don't have that same strong zero-shot and supervised performance within the same model. They are two separate weight files. You might as well have two separate architectures for supervised and zero-shot performance. This problem over here, the X-CLIP supervised model trained for 30 epochs using 8 frames produces a very good 82.3% accuracy on the Kinetics 400 benchmark supervised performance. However, it produces only 41.4% and 67.9% on the HMDB51 and UCF 101 zero-shot settings. However, the X-CLIP zero-shot method, trained only for 10 epochs with 32 frames, produces much better zero-shot performance of 44.6% and 72% on the HMDB and UCF. However, it falls by nearly 4% on the Kinetics 400 supervised performance. We present our methodology, where we freeze the backbone to retain the clip generalization. We then introduce multimodal prompts to improve representation towards the new dataset and the video task. And then we condition prompts to particularly model temporal information. Modal prompting involves visual prompts and text prompts. The visual prompts are at 3 levels of granularity. We have local prompts to model per frame information. We have summary prompts to model a summarized representation across the frames. And then we have global prompts to model the dataset distribution. And then we also have textual prompts to enhance text representation. Diagram of our methodology. Consider a video input to the clip model. So for each frame, we apply a patch embedding. So we get patch tokens over here in green for each frame. And then associated with each frame, we also have a CLS token. Now, first of all, our summary token. To produce the summary token, we apply a self-attention layer between the CLS tokens to produce summary S1 till ST for each frame. Then, for the frame level prompts, we introduce learnable tokens and then condition them on the CLS token for each frame. So the first frame level prompt over here is conditioned on the first CLS for all the frames. Then the second prompt is then conditioned on the second CLS for all the frames, and so on and so forth. So the frame level prompts are conditioned on the CLS tokens of all the frames. And then we have unconditioned learnable global prompts. Similarly, on the text side, we have learnable prompts that are trainable on the text encoder to improve our text representation. And these are the only things that we are training. So the things that we train, the modules that we train, are the summary attention layer, the frame level prompts, the video level prompts, and the text side prompts. And the clip vision encoder and the clip text encoder are kept frozen. Using this multimodal prompting scheme, we achieve state-of-the-art zero-shot performance. We outperform X-CLIP, the previous state-of-the-art, by 4% on HMDB51 and 3% on UCF 101 zero-shot benchmarks. We also achieve competitive supervised performance and better supervised performance compared to the X-CLIP zero-shot model. And this is achieved through a single unified training scheme rather than having separate training scheme for the supervised and zero-shot settings. And we also optimize only 38.8 million parameters as compared to the 131.5 million parameters optimized by X-CLIP. Conclusion. In this paper, we propose a unified model and training scheme for both supervised and zero-shot settings to adapt image text clip models to videos. We achieve state-of-the-art zero-shot performance while still comparable in the supervised setting. And we optimize a much smaller number